Hello, and welcome back to Ontology Explained. I'm Casey Hart, philosopher and ontologist, and today we're talking about OWL restrictions. This is an exciting topic. Without OWL restrictions, you can have a good taxonomy, you can make good connections. With OWL restrictions, you can really flesh everything out. You can make your ontology self-documenting. You can show me what the classes really are, what they mean, what they represent, and you can power all sorts of inference. It's an amazing tool. If you're not using it, you're missing out. And if you watch this video, you won't be missing out any longer. Let's take a look. We're going to start out with OWL restrictions in natural language. Well, I guess not even OWL restrictions yet, but just when we talk about things, understand things, think about the way the world works, how do restrictions function there? The OWL restrictions are going to be a tool in our OWL RDF toolkit to unpack. Then we'll look at basic OWL restrictions, ones that handle sort of your immediate cases. We'll look at blank nodes, which is sort of the technical structure that we have to shove things into. If you aren't familiar with blank nodes at all, I've got another video. I'll link that below in the description here. And then there are a couple of different types of OWL restrictions, ones that are more quantifier based, and then ones that are cardinality based. We'll look at each of those. And then we get complicated. You can put OWL restrictions in OWL restrictions in OWL restrictions with other lists and things showing up. It gets messy. It gets fun. Let's go. In natural language, what the heck are restrictions? To do this, let's talk about another subject that I care a lot about, that I'm passionate about, basketball. So we've got all sorts of basketball players. You've got guards. You got the people who bring the ball up the court, usually primary ball handlers. You've got wings, people who stand out on the sides, still away from the basket. They're more responsible usually for defense, shooting, maybe some cutting. And then you've got the bigs, the ones who sit down in the paint, the ones who protect the hoop, maybe play some post. They get a lot of rebounds. They're taller, as big would suggest. But then we can further break these down, right? Guards, we've got Gary Payton, one of my childhood idols. We've got point guards. Those are the ones who are primarily responsible for bringing the ball up the court. They care much more about assists and keeping turnovers down than they do about shooting, although they do some of that as well. And then you've got shooting guards, on the other hand. They don't bring the ball up as often, although in the modern game, everything's hybrid, so take this all with a grain of salt. Although, if you know enough about basketball to understand that, then you understand the purposes of this for an example anyway. Shooting guard, they care about shooting, as the name suggests. Why am I talking about basketball? This is an ontology channel, of course. But the thought here is that if we're thinking about basketball, you really wanted to understand it, I'm going to tell you about the players. I'm going to tell you about the types of positions. We've got the players, and we've got the bigs, and the centers are a specific type of big. We've got forwards. That's a different type of big. We've got the wings, right? I'm going to start building out a taxonomy. And when we think and describe things, we think about them hierarchically. And this is one thing that OWL-RDF does really well, right? Building taxonomies, building hierarchies. Another thing that's important here when we're defining things is thinking about an Aristotelian structure. So an Aristotelian structure looks like this. We say a species is a genus that has some differentia. So I say a guard is a basketball player that is a ball handler who plays near midcourt. And I can further specify those guards as point guards. The point guards are the guards that have the primary responsibility of bringing the ball up and getting assists. This allows us to nest things and talk about what are the specific differentia that each type of thing that we're interested in has. And then we can put this in OWL-RDF. And this looks great. This is a protege view here. We've got things. More specifically, we got persons. More specifically, we got basketball players and guards and point guards, right? And so this is a set containment thing. So everything that's a point guard is a guard, and everything that's a guard is a basketball player, and everything that's a basketball player is a person, and so on. And this looks pretty good, but we're missing a lot of information, right? In the previous slides, I wasn't just telling you that point guards are guards. I was saying point guards are guards that bring the ball up the court and get a lot of assists and don't want to get turnovers, right? But we're losing that piece. We only know that these are more specific, but we don't know what their differentia are. OWL restrictions to the rescue. Let's see how they help us out. So if we define OWL restrictions, they are anonymous classes, and they're defined by specifying some property or cardinality that every member of that class satisfies. And we create these anonymous classes, and these anonymous classes are going to allow us to fill in those blanks that we were missing on that taxonomy I showed before. They'll allow us to say point guards aren't just guards, they're the guards that care about assists. Let's go to another example, and we'll come back to basketball a lot. Let's talk about pets. There's an adorable raccoon dog up in the corner. And if we want to say that pets are animals owned by people, wonderful. We can do the first part pretty easily, right? That pets are animals. Pets, subclass of animal. And you might be tempted, if you didn't see all of this set up, to say, well, pets are also a subclass of things owned by people. Great. I've said all I need to say. Not really. That's actually a pretty bad approach. The reason it's bad is because we've said things owned by people, and we've created a class for it, but we have no connection to people. We have no connection to ownership, right? We just created a class, and we were hoping you read it and interpret it to mean what we want it to mean. But a good ontology is one that wears its meaning on its sleeve. It's not just that you read it and you understand what the words mean, but you connect all of these types. I want a connection to people. I want a connection to ownership. And to do that, we're going to use an OWL restriction. So it'll look something like this. We'll say a pet is a subclass of an OWL restriction. That's the new type of thing we're creating that is on the property owned by and has some values person. The way you understand that more complicated blank node there is that pets are things that are owned by at least one person. Of course, that's not the complete definition, right? Saying pet is a subclass of that says that every pet's owned by at least one person, but we still need to know that pets are animals, right? So there's more. The subclass relationship gives us necessary conditions. It doesn't give us sufficient conditions. Let's apply the same OWL restriction structure to point guards. So we know that point guards are primary evaluated on their assists and turnover statistics. So we can link point guard as a subclass of two different restrictions. One that they have the primary statistic of assist, another that they have a primary statistic of turnover. Excellent. OWL restrictions to the rescue. Now we're not just getting the nesting structure that point guards are guards. We're saying that point guards are guards that have a primary statistic of assist or a primary statistic of turnover. Blank nodes are important here. We've got those square braces, so we should spend at least a second on that. So OWL restrictions are represented as blank nodes. For example, we can say that human is something that has a human parent. Now, they're almost always blank nodes, but they don't have to be. So here is an example where they're not blank. We could say that there's a human restriction, and that human restriction is an OWL restriction that has parents and human, right? And so we just, instead of putting it all in the blank node on the other end of human, we can create a new thing that is human restriction, and then we can say the same stuff about that. These two things in Turtle syntax are absolutely equivalent. I would almost never do the second one, but there's nothing otherwise wrong about it. So why do we stick with blank nodes most of the time? Well, we don't use a restriction more than once very often. And if you're not going to use it more than once, then why have a specific name for it? We can leave it as an anonymous node. It's also a lot clearer to read in line. So if we go back to this previous slide and we look here, I just prefer the thing on top over the thing that's farther down in terms of representing the human restriction portion. Maybe this is just like a subjective observation. If you look at those two and you feel like the bottom is way clearer, then have at it. I just don't see it that way. And then the third point is that the restrictions are logically important, right? They help us flesh out that taxonomy and what we were talking about earlier, but they're not metaphysically important. And this is tied into why I'm not talking about reusing the restriction over and over again. If I'm not mentioning it again, it's probably because I don't care about the restriction itself so much. I just care about what it means, and using as a blank node gets the meaning across anyway. Okay, so now let's look at the two types of OWL restriction. The first are quantified OWL restrictions. So when I say shooting guard is a subclass of, and we have these has primary statistic pieces, you'll notice we have this OWL has value portion, right? And instead of saying OWL has value, we have three choices. We could say OWL all values from, OWL some values from, or OWL has value. And let's go through each of those in turn to say what they mean. So if we go back to a pet example, and I want to say pet is a subclass of on property owned by, and then some values person, or all values from person. Well, if it's all values from, It means that every pet is such that all of the things it's owned by are people. A weird thing is all values from has no existential import. So if I have this thing right here, and I say of my laser pointer, I don't assert anything about ownership. So it stands in the owned by relation to nothing. It would still be true that all of the things it stands in the owned by relationship to are persons, but it's only vacuously true because there's nothing that it's owned by, when in fact it is mine. I own it. Okay. Some values from does have existential import, and that means that at least one thing owns it, right? Or it stands in the relationship to at least one possible thing. On the other hand, has value specifies an exact triple. So if I want to define Cindy's pet as the things that are owned by Cindy, then I can use this OWL restriction where we have a has value clause as our quantifier. So this just, like I said, specifies the full triple. So if you have Cindy pet in the way that is defined on the top of this slide, and then I know that Fluffy there is a Cindy pet, then I know that it's true that Fluffy owned by Cindy. Okay, cardinality. So we have the quantifier ones, which say how many things, is it all of them, is it some of them, or is it one particular one that you stand in relation to? And then cardinality, we specify numbers. So cardinality restrictions say how many things do you stand in some specified relationship to? So a bachelor is a bachelor in virtue of they stand in the married relationship to exactly nothing. So we can say the bachelor is a subclass of things that are married to no things. So there we don't specify person, right? Yeah, although we'll get to that in just a second. Or we could have owners. Owners are things that own at least one thing, right? And here we can say it's a subclass of on property owns min cardinality 1. That means there's at least one thing they own. We also could do that equivalently by making it a subclass of an OWL restriction where it's OWL some values from and like OWL thing or something like that. That would do the same trick. Now we're going to do a qualified cardinality restriction slide. And qualified cardinality means we specify a number and we also specify the type of thing that it stands in a relationship to. So it's both the cardinality and the class of the cardinality. So a homeowner is someone that owns at least one thing, but it's not just anything, at least one on-class home. So these are more complicated OWL restrictions because they have one extra triple buried within them. It's not just the cardinality piece, it's the cardinality on class, and then we specify the class of things that are owned. Qualified cardinality, it looks this way, different things will support it, but it's gone sort of in and out. It was a later addition to the OWL repertoire and vocabulary. So there are some places that support it, some places that don't support it. I've seen differing reports. I honestly don't know the final decision on whether GraphDB or these like various triple stores will support this right now. So if you want to use qualified cardinality assertions, you should look into a bit, is that supported? That said, it never hurts to put this in. Right? You can use it, you know semantically what the stuff means, and we could build other machinery on your own that implements it. It was an accepted standard at one point. Okay, nesting. And I didn't even realize that there was some sort of owl and nest puns going on here until just now, which is embarrassing because I'm a guy who loves dad jokes. But let's look at some nested owl restrictions. We need more vocabulary because we're going to layer all these different pieces together, and that's what's going to generate these really complex and robust OWL restrictions. So we've got intersection of. That means just what you think we're talking about. Sets, the intersection of two sets are the things that fall into both sets. The union is the stuff that falls into one, either, or both sets. The complement of are things that fall outside of a given set. So the complement of round things are all things that are not round things. OWL one of, we can take a list and then we can specify a whole bunch of things, and OWL one of means it stands in the relation to at least one of the things within that list. For all of the above things, they're list arguments. So for instance, union of, right? We're going to say OWL union of, and then we're going to put parentheses, and then we're going to shove all of the classes that show up in there. And the union of that list is just going to be the things that show up in at least one of all of those various sets. If you have any issues with any of these, go ahead and look up the W3C documentation on them. It's pretty good. There are some examples. Hopefully this is intuitive enough, and we'll see how we can combine, mix and match these with the owl restriction stuff we've covered so far. So one pattern that shows up a ton is when we want to not just say that a point guard is a subclass of something, but we want to define exactly what a point guard is. We need to say what we saw in that Aristotelian definition earlier, right? That point guards are guards that they're guards and they have some differentia to them, right? So the species is genus differentia. So the pattern that shows up when you're writing it in Turtle is to say guard is an equivalent class of the intersection of, and then we put the genus. So first, basketball player. All point guards are basketball players, or in this case, we could say point guards are guards. And then we put the list of all of the various owl restrictions that they satisfy. And so each one of these members of these lists are necessary, but then when you combine them all together, they become sufficient for defining what a point guard is. This pattern I use over and over again. And what's great is once you have an equivalent assertion, then you empower reasoning, right? So if I can prove of someone that they are a basketball player, they do have a primary statistic of assist, and they do have a primary statistic of turnover, then according to this definition, I've proven they're a point guard, right? And that turns out to be really powerful inferentially. Then we can get super complicated. And I've got something up on the slide here, you don't need to squint. I suppose you can try and zoom in and look at it if you want to. I don't worry that much about the legibility. The point here was just to show you in the wild, sometimes the owl restrictions get really nested and complicated, and sometimes that's pretty meaningful. So what you're seeing here is an example where I was defining weather-based stuff, and I wanted to define what hail was. And so hail is something that's made of ice. It's the thing that's moving in a precipitation event, and it's got to be at least, I think it's 0.2 of an inch in size, right? So we want to combine all of those things together. And so when I have my equivalent class assertion, then I say it's equivalent to this intersection. And I've got a bunch of things that show up. And even within some of those things, I have these nested equivalent class or nested owl restriction things going on. If this looks crazy complicated, it is. Don't worry about doing that from the start. But as you keep building more and more simple owl restrictions that say what you want, then you'll get a little more and more courageous and try and bring more things to the table so that you can say exactly what you want to say. But a warning, as it gets more and more complicated, it gets less and less usable. So reasoning works really well on simple owl restrictions, but is less reliable on these complicated ones. And you can probably imagine why that's so, right? If you go back to this slide, or even this slide, if I want to pull back stuff from this, I have the intersection of 3 different things. I can pull back any one of those things and test whether a given entity is a basketball player, or a given entity has a primary statistic of assist. But if I want to look here and prove whether a given thing has a size that is a subclass of, etc., it gets harder. And as that gets harder, reasoning and inference is going to either be slower or maybe not work at all. So as you're making your restrictions more complicated, bear in mind the harder it gets for you to write it and nest it, it might be harder for you to implement reasoning over it as well. And if that's what you're trying to power, just be careful. There are other ways that we can enforce the inference and reasoning, but that's a topic for another presentation, so stay tuned for that one. That was a lot. Let's summarize. Owl restrictions come in 2 flavors. They're property restrictions and they're cardinality restrictions, right? Our property restrictions are when we say all, some, or has a specific value, and then cardinality where we specify how many things it stands in the relation to. And these owl restrictions let us flesh out our class definitions and enable our clear concepts, and we can power inference using them. Owl restrictions are amazing, they're powerful, they're incredibly useful. They're going to take your ontology from a taxonomy with some good connections to something that is really fleshed out, really detailed, and allows you to understand your data more and your machine to understand your data more. Go get it. Go build it. Use some owl restrictions. Play around with them. If you've got questions, if you've got comments, throw them down in the comments below. Like and subscribe to this channel. More videos are coming in your feed. Super excited still to be back and delivering content. Look forward to seeing you next time. Thanks.